Okay, chemists, in this crash course, we are going to look at the things you might need to know for aqueous reactions. This was the unit in which we started to introduce molarity. Remember, molarity, capital M, is the moles of solute per liters of solution. Most of the time, we will probably use millimoles because they're given milliliters. We hardly ever talk about liters of things in this level of the class. And then why did we learn molarity? Well, molarity times volume, when you multiply those two, that's a way of getting the moles of a substance. So the dilution equation, M1V1 is equal to M2V2, just says moles equals moles. Or the titration equation, molarity of acid, volume of acid, is equal to molarity of base, volume of base, because acid-base reactions typically react in a 1-to-1 ratio, so that's moles of acid equal the moles of the base as reactants. Then we talked about different types of reactions, and there are three that we looked at: precipitations, acid-base reactions, and redox reactions. Precipitations means you need to know your solubility rules, the NAG-SAG list. That is the nitrates, acetates, and group 1. So anything with a nitrate, anything with a C2H3O2 negative, and anything with a group 1 ion, such as sodium or potassium, will always be a soluble ion. I said NAG-SAG, that's only the first half. The SAG, S-A-G, stands for sulfates, ammoniums, and group 17. So sulfates, if you've got an SO42-, usually soluble. Ammonium, NH4+, in group 17. Halides, chlorides, bromides, iodides. There are some exceptions. So except for sulfates, except things like calcium, barium, and then silver, lead, and mercury. Same with the halides, except with silver, lead, and mercury. But otherwise, if you see a reaction or you see a compound and it contains one of these NAG-SAG ions, those are going to be spectator ions, and thus you get a soluble compound. So if we had the reaction of, hypothetically, silver nitrate, AgNO3, plus potassium chloride, KCl, and I'm asked to think about what the products are so I can do some kind of stoichiometry, I cross out the spectator ions, the nitrate and the potassium, and I'm left with silver ion and chloride ion, which means my reaction is really just Ag plus Cl minus makes AgCl. That's how you write a net ionic reaction. The same kind of thinking can be used for acid-base reactions. Acid-base reactions, we also get rid of the spectator ions. For example, if I have hydrochloric acid, HCl, plus sodium hydroxide, NaOH, I get rid of spectator ions, in this case sodium ion and chloride ion, and my net ionic would be H plus OH minus makes H2O. If I had a similar case with, let's say, hydrochloric acid, or let's actually change hydrochloric acid, let's make it acetic acid, HC2H3O2, plus a strong base, KOH. This time we have to know which acids are weak and which acids are strong. Acetic acid is not a strong one, it is a weak one. Therefore, it stays together. It's not dissociated. That actually means what we should do is recap our weak and our strong acids and bases. You really just need to know the strong ones. So strong acids. There are 7 that you should know. HCl, HBr, HI, sulfuric, nitric, perchloric, and chloric. Those are the strong. If it's not one of those 7, you can assume it's weak. So if we have a reaction with a strong acid, it totally dissociates. Strong acids are analogous to soluble salts. They completely dissociate. Lastly, we looked at redox reactions. Redox reactions are just the ones that have changes in oxidation state. So maybe I see the reaction of peroxide and iron 2. and I turn that into iron 3 and an oxygen. Let's make that a water, actually. And I can assign oxidation states. In a peroxide, oxygen is -1, H is +1. In iron 2 plus, it's +2. In iron 3 plus, it's +3. In water, it's -2 and +1 for the oxygen and hydrogen. So the oxygen gets reduced, the iron gets oxidized. So oxygen is getting reduced, iron is oxidized. And we don't have to, but we could talk very quickly about balancing these reactions. Let me just write that again. Peroxide plus iron 2 makes iron 3 and water. And I look at the changes in oxidation state. Oxygen goes from -1 to -2. So each oxygen gains 1 electron, but we're going to have 2 of them because there's 2 in this formula, which means I need at least a 2 in front of the waters over here. So I have a change of 2 electrons. The iron changes by just 1 electron. So that means for whatever half reaction I would have involving peroxide turning into 2 waters, and the analogous half reaction I have iron 2 turning into iron 3, the iron reaction is going to have 1 electron in it. The oxygen reaction is going to have 2 electrons in it. That means I need to normalize the iron reaction and double everything with an iron in it. So I actually put 2's in front of those irons. And then you balance the rest by inspection. I'll just clean this up by getting rid of those little oxidation states just to make it a little neater once we're sure we have those. And to do this, you balance the charge. If we're in acid, I see 4 plus on the left, but 6 plus on the right. So I would need another 2H plus on the left, and then I balance the rest with water molecules if needed. But it turns out this one's actually already done. That's your completely balanced reaction. You can always check. 2 plus 2 is 4 H's, 4 H's on the right. 2 oxygens on the left, 2 oxygens on the right. 2 irons on the left, 2 irons on the right. Total charge, 2 plus 4 plus makes positive 6. And on the right we have positive 6, so this is a balanced redox reaction. That type of balancing, however, is not on the AP. Even though you might know how to do it, we don't actually need to do that for the AP exam. We really just need to know how to identify a redox reaction. So let's look at some practice questions, and then we'll wrap up this crash course. Here's some multiple choice. First, a half a liter solution of sodium phosphate is made with 82 grams. What's the molarity? So molarity is moles per liter. Your moles is your mass over your molar mass, and they give us 82 grams, and they're very nice. They give us the molar mass of 164. The volume of solution in liters is 0.5, half a liter, so I need to turn those into easier numbers. Well, look at that numerator. That's just a half. So this is 0.5 over 0.5. So this is 1 molar. Math that you can do without a calculator. Very common on the AP. Let's try the one below it. A student combines 50 mils of 1 molar sodium chloride with 50 mils of 1 molar silver nitrate. So let's think about the reaction we have. Chloride plus silver ion makes AgCl. And they gave us a volume and a molarity. You multiply those two, you get millimoles. So we have 50 millimoles of chloride, and we have 50 millimoles of silver. This is a limiting reactant problem, but they're equally limiting. We're going to run out of both. They repeat the experiment, and instead they use 50 mils of 2 molar NaCl. They're going to double this. So they're going to change this 50 to 100 millimoles. Still limiting reactant, but now we're specifically limiting it in the same amount of silver. How much precipitate would you get? Well, it's going to be based on that 50 millimoles, no matter which experiment you're talking about. So, scanning the choices, it does not change because the amount of silver nitrate did not change. It doesn't double, and it changes, but not because the coefficients are 1. That's not what we're looking at. Moving on, what's correct about the reaction of zinc plus HCl makes zinc chloride and hydrogen? This is not a combustion, this is not a double or acid-base, this is a redox reaction, and you can tell because the oxidation states change from 0, +1, -1 to +2, -1, and 0 for those respective elements. Also, anytime a reaction contains a neutral element, you know it's a redox reaction because it goes from a state of 0 to not 0. So that's a quick way of just identifying a redox. Okay, last multiple choice. A student gets a 10-gram sample of a powder that says it's solid barium chloride. They add some water, and then they add excess sodium sulfate. They get a precipitate and dry it to its constant mass. What question could best be answered using this? Is the sodium sulfate pure? Is the barium chloride pure? What's the solubility of the barium compound or the other barium compound? Well, let's think about what they've got. They're making some mass of barium sulfate, and they get that number. And then they know the 10 grams of the original substance. So if this is a pure barium chloride sample from the beginning, they would actually be able to calculate how many grams of barium sulfate they get as a precipitate. It's 1-to-1, barium to barium, plus it's excess sodium sulfate. So this number that they get experimentally should match what they would get based on that. So the correct answer sounds like they're not even having us calculate it, but they're having us identify that this is a sample of, this is a question of, is it pure? Is the barium chloride going to be pure? Okay, let's wrap up with one free response question. Consider the two mixtures of the same volume. One is 0.2 molar sodium chloride, one is 0.1 molar but calcium chloride. Complete the drawing by adding a particle diagram for the calcium chloride. Well, here we're going to count what we've got. It looks like I've got 1, 2, 3, 4, 5, 6, 7, 8 chlorides, and then 8 sodium ions, and this is 0.1 molar. So I want this to be twice the molarity of those ions in, or sorry, half the molarity. This is 0.2 molar, and this is 0.1 molar calcium chloride. So I need this to be half the molarity. That would mean, let's see, and it's also not a 1-to-1 ratio, but the cation is still a 1. So I'm going to need half as many cations. So I'm going to draw little black circles, because that's what it tells me to draw. And instead of 8 of them, I'm going to draw 4 little unfilled circles for the calciums. So I should have 4 calciums. And then I should have the same amount of chloride, actually. It's a 2-to-1 ratio of chloride to calcium. So I'm going to have, looks like 8 calciums. 1, 2, 3, 4, 5, 6, 7, 8. And then I can tell looking at that, that's probably very easy for a grader to grade. So they designed this question to test the concept, but also to make it easy to grade. They just have to look for 4 of those instead of 8, and a nice quick count of the same number of the dark ones. So lots of times the AP will ask you to draw a particle diagram. It's never a difficult question, but they're going to be really specific about what they want. So that's a good example of that. Okay, that's a quick crash course of some of the things you might need to know about molarity and aqueous reactions.